So we will now start discussing lesson 3, wherein we will talk about resiliency patterns. So this lesson introduces patterns related to the resiliency of workloads in Azure. So after completing this lesson, we will be able to describe the transient errors, we'll be able to describe the circuit breaker pattern, retry pattern, and describe the queue-based load leveling pattern. So let's start with transient errors. So one of the primary differences between developing application on-prem and in the cloud is the way you design your application to handle transient errors. Transient errors are those errors that occur due to temporary interruptions in the service or due to excess latency. Many of these temporary issues are self-healing and can be resolved by exercising a retry policy. So retry policies define when and how often a connection attempt should be retried when a temporary failure occurs. Simply retrying in an infinite loop can be just as dangerous as infinite recursion. So a break in the circuit must eventually be defined so that the retries are aborted if the error is determined to be of a serious nature and not just a temporary issue. Transient fault handling is a pattern that makes your application more resilient by handling temporary issues in a robust manner. This is done by managing connections and implementing a retry policy. This pattern is already implemented in many common .NET libraries such as Entity Framework and the Azure Software Development Kit. This pattern is also implemented in the Enterprise Library in such a manner that it can be brought into a wide variety of application scenarios. Next, we will move on and discuss the circuit breaker pattern. So circuit breaker pattern handles faults that might take variable amount of time to recover from when connecting to a remote service or resource. This can improve the stability and resiliency of an application. So what is the context and problem? So in a distributed environment, calls to remote resources and services can fail due to transient faults such as slow network connections, timeouts, or the resource being overcommitted or temporarily unavailable. These faults typically correct themselves over a short period of time, and a robust cloud application should be prepared to handle them by using a strategy such as the retry pattern. However, there can also be situations where faults are due to unanticipated events, and that might take much longer to fix. These faults can range in severity from a partial loss of connectivity to the complete failure of a service. In these situations, it might be pointless for an application to continually retry an operation that is unlikely to succeed. And instead, the application should quickly accept that the operation has failed and handle this failure accordingly. Additionally, if a service is very busy, failure in one part of the system might lead to cascading failures. For example, an operation that invokes a service could be configured to implement a timeout and reply with a failure message if the service fails to respond within this period. However, the strategy could cause many concurrent requests to the same operation to be blocked until the timeout period expires. These blocked requests might hold critical system resources such as memory, threads, database connections, and so on. Consequently, these resources could become exhausted, causing failure of other possibly unrelated parts of the system that need to use the same resources. So in these situations, it would be preferable for the operation to fail immediately and only attempt to invoke the service if it's likely to succeed. You need to note that the setting is shorter timeout might help to resolve this problem, but the timeout shouldn't be so short that the operation fails most of the time, even if the request to the service would eventually succeed. So what is the solution to this contextual problem? So the circuit breaker pattern, popularized by Michael Nygaard, in his book Release It, can prevent an application from repeatedly trying to execute an operation that's likely to fail, allowing it to continue without waiting for the fault to be fixed or wasting CPU cycles while it determines the fault is long lasting. The circuit breaker pattern also enables an application to detect whether the fault has been resolved. If the problem appears to have been fixed, the application can try to invoke the operation. So a circuit breaker acts as a proxy for operations that might fail. The proxy should monitor the number of recent failures that have occurred and use this information to decide whether to allow the operation to proceed or simply return an exception immediately. So the proxy can be implemented as a state machine with following states that mimic the functionality of an electric circuit breaker, like closed, half open, and open. When we talk about closed, the request from the application is routed to the operation. The proxy maintains a count of the number of recent failures, and if the call to the operation is unsuccessful, the proxy increments this count. If the number of recent failures exceed a specified threshold within a given time period, the proxy is placed into the open state. At this point, the proxy starts a timeout timer, and when this timer expires, the proxy is placed into the half-open state. Then you have the open state. So the request from the application fails immediately and an exception is returned to the application. That's the open state. Then you have the half open state, wherein a limited number of requests from the application are allowed to pass through and invoke the operation. If these requests are successful, it's assumed that the fault that was previously causing the failure has been fixed, and the circuit breaker switches to the closed state. The failure counter is reset. So if any request fails, the circuit breaker assumes the fault is still present, so it reverts back to the open state and restarts the timeout timer to give the system the further period of time to recover from the failure. The half-open state is useful to prevent a recovering service from suddenly being flooded with requests. As a service recovers, it might be able to support a limited volume of requests until the recovery is complete. But while recovery is in progress, a flood of work can cause the service no timeout or fail again. So in this figure, the failure counter is used by the closed state is time-based. It's automatically reset at periodic intervals. This helps to prevent the circuit breaker from entering the open state if it experiences occasional failures. The failure threshold that tips the circuit breaker into the open state is only reached when a specified number of failures have occurred during a specified interval. The counter used by the half-open state records the number of successful attempts to invoke the operation. The circuit breaker reverts to the closed state after a specified number of consecutive operation invocations have been successful. If any invocation fails, the circuit breaker enters the open state immediately and the success counter will be reset the next time it enters the half-open state. The circuit breaker pattern provides stability while the system recovers from failure and minimizes the impact on performance. It can help to maintain the response time of the system by quickly rejecting a request for an operation that's likely to fail rather than waiting for the operation to time out or never return. If the circuit breaker raises an event each time it changes state, this information can be used to monitor the health of the part of the system protected by the circuit breaker or to alert an administrator when a circuit breaker trips to the open state. The pattern is customizable and can be adapted according to the type of possible failures. For example, you can apply an increasing timeout timer to the circuit breaker. You can place the circuit breaker in the open state for a few seconds initially, and then if the failure hasn't been resolved, increase the timeout to a few minutes and so on. In some cases, rather than open state returning failure and raising an exception, it could be useful to return a default value that is meaningful to the application. Next, we move on to the retry pattern. So retry pattern enables an application to handle transient failures when it tries to connect to a service or network resource by transparently retrying a failed operation. This can improve the stability of the application. So what is the context and problem? An application that communicates with elements running in the cloud has to be sensitive to the transient faults that can occur in this environment. Faults include the momentary loss of network connectivity to components and services, the temporary unavailability of a service, or timeouts that occur when a service is busy. These faults are typically self-correcting, and if the action that triggered a fault is repeated after a suitable delay, it's likely to be successful. For example, a database service that's processing a large number of concurrent requests can implement a throttling strategy that temporarily rejects any further request until its workload has eased. An application trying to access the database might fail to correct, but if it tries again after a delay, it might succeed. So what is the solution? So in the cloud, transient faults aren't uncommon, and an application should be designed to handle them elegantly and transparently. This minimizes the effect faults can have on the business task an application is performing. If the application detects a failure when it tries to send a request to a remote service, it can handle the failure using following strategies. The first strategy is cancel. If the fault indicates that the failure isn't transient or is unlikely to be successful if repeated, the application should cancel the operation and report an exception. For example, an authentication failure caused by providing invalid credentials is not likely to succeed no matter how many times it's attempted. Then you have the retry strategy. So if the specific fault reported is unusual or rare, it might have been caused by unusual circumstances such as network packet becoming corrupted while being transmitted. In this case, the application could retry the failing request again immediately because the same failure is unlikely to be repeated and the request will probably be successful. And finally, you have retry after delay. The fault is caused by one of the more commonplace connectivity or busy failures. The network or service might need a short period while the connectivity issues are corrected or the backlog of work is cleared. The application should wait for a suitable time before retrying the request. For the most common transient failures, the period between retries should be chosen to spread requests from multiple instances of the application as evenly as possible. This reduces the chance of a busy service continuing to be overloaded. If many instances of an application are continually overwhelming a service with retry request, it will take the service longer to recover. If the request still fails, the application can wait and make another attempt. If necessary, this process can be repeated with increasing delays between retry attempts until some maximum number of requests have been attempted. The delay can be increased incrementally or exponentially depending on the type of failure and the probability that will be corrected during this time. So the following diagram in this slide illustrates invoking an operation in a hosted service using this pattern. If the request is unsuccessful after a predefined number of attempts, the application should treat the fault as an exception and handle it accordingly. Next, we will move on to the next pattern, which is queues. So you use a queue that acts as a buffer between a task and a service it invokes in order to smooth intermittent heavy loads that can cause the service to fail or the task to time out. This can help to minimize the impact of peaks in demand on availability and responsiveness for both the task and services. So what is the context and problem here? So many solutions in the cloud involve running tasks that invoke services. In this environment, if a service is subjected to intermittent heavy loads, it can cause performance or reliability issues. A service could be part of the same solution as the task that uses it, Or it could be a third-party service providing access to frequently used resources such as a cache or a storage service. If the same service is used by a number of tasks running concurrently, it can be difficult to predict the volume of requests to the service at any time. So a service might experience peaks in the demand that cause it to overload and be unable to respond to requests in a timely manner. Flooding a service with a large number of concurrent requests can also result in the service failing if it's unable to handle the contention these requests cause. What is the solution to this problem? So refactor the solution and introduce a queue between the task and the service. The task and the service run asynchronously. The task posts a message containing the data required by the service to a queue. The queue acts as a buffer, storing the message until it's retrieved by a service. The service retrieves the message from the queue and processes them. Requests from a number of tasks, which can be generated at a highly variable rate, can be passed to the service through the same message queue. This figure in this particular slide shows using a queue to level the load on a service. So the queue decouples the task from the service, and the service can handle the message at its own pace regardless of the volume of requests from concurrent tasks. Additionally, there is no delay to a task if the service isn't available at the time it posts a message to the queue. So this pattern provides various benefits. It can help to maximize availability because delays arising in service won't have an immediate or direct impact on the application, which can continue to post messages to the queue even when the service isn't available or isn't currently processing messages. It can help to maximize scalability because both the number of queues and the number of services can be varied to meet demand. It can help to control cost because the number of service instances deployed only have to be adequate to meet average load rather than the peak load. So some services implement throttling when demand reaches a threshold beyond which the system could fail. Throttling can reduce the functionality available, and you can implement load leveling with these services to ensure that the threshold isn't reached. So this was queue-based load leveling pattern. The question that you need to discuss is, if you were to design a retry policy to connect to an instance of Azure SQL database, what parameters like cool-off time, max retry count would you use? So think about it and come up with an answer. In the next video, we will move on to the next topic and we will discuss lesson 4.